There's something that needs to be said, even if it's not what most people following Matt Armstrong's project want to hear, and it centers on a single decision that could end up being far more important than it currently seems. Choosing to use the repaired, welded bracket instead of going with a CNC machined replacement might feel justified given the circumstances, and it's easy to understand why that path was taken. But it also introduces a level of risk that simply didn't need to exist. This isn't about questioning the quality of the work itself, because the craftsmanship involved in that repair is undeniably impressive. The weld was carried out to a very high standard, and the reinforcing additions arguably improved on what the original manufacturer produced. However, even exceptional workmanship cannot fully erase certain inherent risks tied to the nature of welding itself, and that's where the concern lies. The issue isn't something that would show up immediately either. At idle, during basic operation, or even on a light test drive, everything can appear perfectly fine. The engine can run smoothly, the car can behave as expected, and nothing would seem out of place. The real test only comes later, under full load, when the car is pushed to the level it was actually built for. That's when the hidden variables begin to matter, and by that point, if something goes wrong, it won't be a minor inconvenience, but potentially a catastrophic failure. To be clear, none of this is about discrediting the people involved. What has been accomplished in rebuilding such a complex machine, without direct factory backing, without access to official documentation, and without manufacturer support, is genuinely remarkable. It speaks to a high level of skill, determination, and problem-solving ability. But even within an extraordinary project, there can be individual choices that deserve scrutiny, and this bracket decision is one of them. The reasoning behind opting for the repair instead of a new CNC machined part wasn't careless or uninformed. In fact, it was grounded in a very real concern about precision. The bracket in question is responsible for holding crank position sensors, which are absolutely critical for engine operation. These sensors inform the engine control unit about the exact position and timing of each cylinder, which directly affects ignition timing, fuel delivery, and overall performance. Even a slight deviation in their placement could lead to serious issues, ranging from poor performance to complete engine failure to start. Given that, the hesitation around relying on a CNC reproduction based on scanned data makes sense. If the geometry wasn't replicated perfectly, the consequences could be immediate and obvious. However, focusing on that concern may have overshadowed a different kind of risk, one that doesn't show up right away and can't be easily measured before installation. When a welded repair is made to a cast component, the result is not a uniform material. Instead, you end up with regions that have fundamentally different characteristics. The original casting was created under controlled conditions, with specific cooling rates and treatments designed to achieve particular material properties. The weld, on the other hand, is introduced later under entirely different conditions, and even when done correctly, it forms a distinct structure. Between these two regions lies what engineers refer to as the heat-affected zone. This area is neither the original material nor the weld itself, but something altered by the heat of the welding process. Its properties are changed in ways that aren't always visible or easily predictable. Under normal, low-stress conditions, this difference may not matter much. The part can perform its function without any noticeable issue, and everything can seem reliable. The problem arises under repeated stress, especially the kind experienced in a high-performance engine. When the engine is operating at full power, the forces involved are not only high, but constantly changing. Components are subjected to cycles of loading and unloading, with stresses reversing direction rapidly. Over time, these cycles can lead to fatigue, particularly in areas where the material properties are inconsistent. The heat-affected zone becomes a potential weak point, not because of poor workmanship, but because of how the material behaves under these conditions. Cracks can begin to form at a microscopic level, gradually growing with each stress cycle until they reach a point where failure occurs. A CNC-machined bracket, by contrast, would have been made from a single piece of material with consistent properties throughout. There would be no welds, no transitions between different material states, and no heat-affected zones. That uniformity significantly reduces the likelihood of fatigue-related issues developing over time. It doesn't make the part indestructible, but it removes a specific category of risk entirely. The argument that the CNC option might introduce inaccuracies in sensor placement is valid, but it's also a problem that can be addressed through proper verification. Precision measurement tools can confirm whether the critical dimensions match the required specifications before the part is ever installed. If discrepancies are found, adjustments can be made in the manufacturing process, and the part can be remade until it meets the necessary tolerances. This iterative capability is one of the strengths of CNC machining and allows for a level of confidence that isn't dependent on assumptions. In contrast, once a welded repair is completed, the internal characteristics of the material can't be easily inspected or altered. The heat-affected zones are simply part of the structure, and their long-term behavior can only be revealed through use. That means the risk isn't something that can be eliminated beforehand, it can only be managed. At this point, with the repaired bracket already installed and the car operational, the focus shifts to how to minimize that risk going forward. Gradual testing becomes essential. Instead of immediately pushing the car to its limits, it would be far safer to increase the load incrementally over time. This allows any potential issues to surface in a more controlled manner. Regular inspections during this period are also crucial, as early signs of cracking or material fatigue might be detectable before a complete failure occurs. Paying attention to subtle changes, such as new vibrations or irregular sensor readings, can provide early warnings that something isn't right. Ultimately, this situation highlights a broader reality about high-level independent projects. It's not just about having the skill to execute complex tasks, but also about having the resources and flexibility to choose the safest possible approach every time. Time constraints, financial considerations, and external pressure can all influence decisions, sometimes leading to choices that prioritize practicality over long-term certainty. That doesn't mean those choices are reckless, but it does mean they carry trade-offs. In this case, the repaired bracket represents a solution that works and was achievable within the constraints at hand, but it also carries a lingering uncertainty that a different approach might have avoided. Whether that uncertainty ever translates into an actual problem remains to be seen. It's entirely possible that the repair will hold up indefinitely, performing flawlessly under all conditions, and proving that the concern was overstated. But it's also possible that the underlying risks will only become apparent after extended use, particularly under demanding conditions. The outcome will ultimately provide the answer, not speculation or debate. Until then, it's reasonable to acknowledge both the impressive achievement of getting the car running and the fact that one aspect of the build carries a level of risk that can't be fully